Right. Hello, everyone. So we have about 3 weeks left in the semester. Yikes, that's absolutely wild. We are going to spend those last few weeks talking about, the really big stuff in the universe, right? Galaxies and Big Bang cosmology. We will start this journey by looking at our own galaxy, right, known as the Milky Way. So the Milky Way, of course, is the galaxy we live in. It's really the only galaxy we can't view from the outside. I think this is something we don't think about too often, because we have all these great telescopes that are gathering data millions and millions of light years away. But we ourselves have never left the galaxy. The furthest we've actually sent something is Voyager 1 and 2, which I think are considered to be in interstellar space now. So actually out of the solar system, but that distance is not even close to what we need to get a bird's eye view of our galaxy. So on this slide here, this is how we must view the Milky Way, right, from the inside. So this presents some challenges to studying the Milky Way, though not insurmountable ones. One of the most obvious questions we can ask is about the structure of the galaxy. So the first people to kind of figure out kind of the general shape of the Milky Way was William and Caroline Herschel. So William, we've talked about before. Caroline was his sister, an accomplished astronomer in her own right. So they observed that most stars that we see lay in like a kind of flattened structure encircling the sky, and that the number of stars were roughly the same in all directions. So they concluded from this that the sun is actually in the center of a stellar system that's the shape of a wheel. So this is kind of the map they ended up drawing. This is from William Herschel's book on the subject. And I mean, given the kind of the constraints of observations and thinking at the time, this is not a bad conclusion to reach. We know now, of course, that the Milky Way is what we call a spiral galaxy, but the sun is not at its center, far, far from it. The sun and the solar system are about 25 to 30,000 light years from the center. The structure of the Milky Way can be broken down into kind of three broad categories. We have disks and halos, the spiral arms, and the central supermassive black hole. So let's start off by talking about the disks and halo. So the disk of the Milky Way is relatively thin and rotating, right? Our sun takes 250 million years to travel around the galaxy once. It's about 100,000 light years across and about 2,000 light years thick. Um, it's mostly made of young stars, gas, and dust. And so rather than disk, I should really say disks, plural, because if you study the Milky Way carefully, you will see that there is a thin disk embedded in kind of a puffier thick disk. You can kind of see that in this drawing illustration right here. You can see it's a little bit darker, kind of in this area. This would be the thin disk, and this kind of puffy area along the outside. That is the thick disk. So we're going to see next week probably that galaxies come in a lot of different shapes. But even within a class of galaxy, there are differences. So the Milky Way is a spiral galaxy. And on the screen here, it says obviously not a picture, an illustration of what we think the galaxy looks like. A lot of spiral arms. So some spiral galaxies are fairly flat, consisting mostly like all disk, right? Kind of like a frisbee, just flat. Others contain an almost spherical region of older stars at its center called the bulge. And still other spiral galaxies have something in the center called a bar, which is an elongated region of older stars. So the Milky Way doesn't fall neatly into these categories. It has what's described, or I've seen described as a quote unquote bulgy bar. So a classic bulge is more of a sphere, like someone cut a hole in a frisbee and stuck a tennis ball in it. Um, the Milky Way's bulgy bar is kind of more elongated, like a bar, kind of like a cigar shape. Um, and it's thicker and puffier than we normally expect a bar to be. So this cyan oval right here is our bulgy bar, right? It's a little too elongated to really be considered a classic bulge. It's a little too puffy to be considered kind of a classic bar. Having a bulge, or in our case, a bulgy bar, doesn't mean that a spiral galaxy can't also have a classic bar. So astronomers have identified a bar in the center of the Milky Way as well that is very creatively called the long bar. So this orange oval here represents the long bar. So the Milky Way is considered to be a barred spiral galaxy, even though the exact nature of the bulge and the bar are really still being worked out. There is very clearly more of a bar-like structure in the center of the Milky Way. One thing you should take away from this, though, is that the center of the galaxy, whether we call it a bar or a bulgy bar or whatever, is that it mostly consists of yellow and red stars, and that there is too much dust to see through to the center using visual wavelengths. We can only see through the dust really in the infrared. The galaxy does extend beyond the disk into something called the halo. So this is kind of roughly spherical, maybe kind of more a little bit football-y shape, but kind of, that just a rough kind of circular shape. Um, it's that circular spheroidal shape of old stars that extends about 150,000 light years from the center. So this is just a drawing, obviously very exaggerated as far as what the bulge looks like. So we have a thin disk, right, with stars and gas, a thick disk here that has mostly stars. Most of the gas is in the thin disk. Then we have a bulge, or in the Milky Way's case, a bulgy bar that's stars. And then we have this halo of other stars, kind of a diffuse halo. This is where globular clusters like to live, like really dense regions of stars. We have the spiral galaxy, these spiral shapes, this disk embedded in this more spherical region of diffuse stars. The galaxy, though, is also embedded in a larger dark matter halo. So we'll talk a little bit more about the Milky Way's dark matter in a bit, but this halo extends about 200,000 light years from the center and can't be directly observed with light. So this illustration here shows kind of the extent of dark matter as opposed to the luminous matter that we can see. So we have luminous matter right here, kind of its halo around here, and then out here we have a significant amount of dark matter, so matter we can't see. Next, let's look at the Milky Way's spiral arms. So it's been difficult to determine just how many arms the Milky Way has. Our most recent depiction of the galaxy shows two main spiral arms, but this is still a little controversial. But for our purposes, the Milky Way has two main arms, one that extends from each end of the bar. So we have kind of this bar right here We have one of the main arms coming out this way from this end, and the other one coming out this way, like this. So the two main arms are the Scutum Centaurus arm and the Perseus arm. But you can see just on the slide here, there are several other arms, like the Norma arm here, Sagittarius. We have the near 3 kiloparsec arm and the far 3 kiloparsec arm, outer arm. Uh, it's a complex structure here. We have two main arms, but a lot of smaller arms and so-called spurs. So the sun is right here in what's called the Orion spur of the Orion Cygnus arm. So you can see we're about halfway between the center of the galaxy and the edge. So how do these spiral arms form? So think back to Kepler's third law of planetary motion. So planets closer to the sun move faster than planets further away. Stars and interstellar dust obey this same law. So the matter in larger orbits trails behind the matter in smaller orbits. So this leads to something called differential galactic rotation. And as it turns out, regardless of the original distribution of material, differential rotation can stretch it out into spiral arms. So galaxies can evolve spiral arms over time. We will see not all galaxies are spiral galaxies, but spiral structure is a completely natural form for a galaxy to take. And this is an illustration actually from your book on how a spiral structure might form from irregular clouds in this interstellar material. The final component of Milky Way structure I'd like to talk about is the central supermassive black hole that we call Sagittarius A star. So this A with an asterisk, that's pronounced A star. So black holes, remember, don't give off any light. And since the black hole is in the center of the galaxy, all visible light around it is absorbed by dust anyway. But we can look, in wavelengths like the radio and the infrared to get a peek at kind of the area around the black hole. So Sagittarius A is a bright radio source at the center of the Milky Way. So this picture right here on this slide, this is the entire region, Sagittarius A. So this is the bright radio emission is from gas heated up by hot stars and supernova remnants, right? There's no star formation here, but there's lots of dust and molecular gas revolving around the black hole, at least what we think is the black hole. And on this, I think this is a really cool image. These circles right here, these are basically supernova remnants. They're, exploded stars. And right here, kind of the brightest spot in this bright radio image is what we call Sagittarius A star. So we see this stuff orbiting around some central spot in our galaxy that we call Sagittarius A star. But how do we know that it's a black hole and not something else, like a really, really big star cluster, for example? So we know this from the observed orbits of stars. So using Kepler's third law again, we can calculate the mass of the central object, keeping stars in orbit. So by analyzing the motions of stars near the center of the galaxy, astronomers Reinhard Genzel and Andrea Gades determined that the thing at the center of the galaxy was too massive to be anything other than a black hole. So in fact, this analysis told us that something like a 4.6, something that's 4.6 million times the mass of the sun is sitting in a region that's 17 light hours across. So it takes 17 hours for light to travel from one end to the other. And this is a simulation here of kind of their data, like what they looked at over several years, the orbits of these stars that are close by to this dense thing, whatever it is in the center of the galaxy that they determined to be a supermassive black hole. So more evidence came when we studied the accretion disk around a black hole. So matter will spiral in to a black hole, or at least spiral around the black hole. And that matter, while it's doing that, is heated and forms a disk that emits at radio wavelength. And we call this an accretion disk. So by measuring the size of this disk, we can show that the diameter of the radio source, Sagittarius A star, is actually 0.3 AU, which is the size basically of Mercury's orbit, or 2.5 light minutes across. So think about that. There is a 4.6 million solar masses squished into an area that can be encompassed by Mercury's orbit. That's really, really massive, really, really dense. In 2022, the Event Horizon Telescope, a telescope whose purpose is to kind of image, a quote unquote image black holes as kind of the area around it. It got this really cool picture of Sagittarius A star, and they did it again in 2024. Exposing kind of the magnetic field lines around the black hole. So we call this the black hole's shadow. It's essentially the closest thing we can possibly get to actually photographing a black hole. Okay, so now we know the structure of the Milky Way, right? It's a spiral galaxy with a disk of stars, a bulgy bar, and a supermassive black hole at its center. So now you might be wondering, how much does it weigh? And how do you even go about weighing a galaxy? Well, guess what? You can use Newton's version of Kepler's third law. So the galaxy is a disk, right? And everything in it, including the sun, is orbiting around the center. We can consider the sun's orbit basically circular. So we can maybe the sun will follow basically this yellow circle around the center of the galaxy for a couple 100 million years. We can also treat all mass lying closer to the center of the sun as being concentrated at the center. So we can treat everything kind of within this circle as concentrated at the center. So this is a little counterintuitive, but this is how the math works out for this. So we can rearrange the equation a little bit to get what we have on this slide right here, where we can get M is the mass of the large central object. V is the velocity, in this case, of the sun. R is the distance of the sun from the center, and G is a gravitational constant. So when you plug in values for V and R, we can get the mass of all of the matter within this circle, like within the sun's orbit. So there are stars and gas and stuff outside the sun's orbit, right? We can see it all right here. But the amount of luminous matter, right, the matter that we can see, drops off dramatically towards the edge of the galaxy. So if luminous matter was all that there was in the galaxy, actually this would give us a pretty good estimation for the mass of the galaxy. But it isn't a good estimation. So why would that be? So according to Kepler's third law, objects orbiting at large distances should move more slowly than objects closer in. But that's not what we see. So at large distances from the luminous boundary of the galaxy, the stuff is not moving more slowly than the sun. So there must be more matter that we can't see. So on your screen here are a couple of examples of what we call a galaxy rotation curve. This is the speed that a galaxy is going, or speed that basically the objects, the stars and things that in the galaxy are moving on the y-axis here. And then the distance from the center of the galaxy is on the x-axis. So if there were no dark matter, we would expect the stars in the center to go around much faster than the stars at the edge. We expect this red line right here. This is our expectations. Much faster speeds towards the center, and going down very quickly as we move out from the center of the galaxy. But that doesn't actually fit our observations. Instead, the rotation curve is flat. We get something like this in the data. Right down here, this plot, this is actual from an actual paper, Rose et al., measuring the rotation curve of the Milky Way. And you can see it is basically flat. It goes down just a little bit, but it doesn't meet these expectations of a precipitous decline. It does remain pretty flat. So this indicates that there's more mass in the outskirts of the galaxy than we can see. So this is what astronomers call dark matter. We can't see it. It doesn't interact with electromagnetic radiation. We know about it through observations like this, right? Basically through gravitational observations. So by studying the motions of those globular clusters that kind of live in the outskirts of the luminous matter of the galaxy, astronomers have shown that the total mass of the Milky Way is something like 2 trillion times the mass of the sun, so 20 times greater than the mass of the luminous matter. Okay, so we're getting towards the end of this lecture, and I want to shift gears a little bit and talk about how the Milky Way formed. We'll talk a little more about galaxy formation and evolution next week, but for now, the important thing to understand is that the Milky Way, as we know it today, is the product of multiple mergers with smaller galaxies. The universe is moving all the time. Galaxies will collide into each other, and they will merge together. So we are at the moment undergoing a merger with the Sagittarius dwarf galaxy. It's much smaller than the Milky Way, about 10,000 times less massive, and it will complete this merger in the next 100 million years or so. So this has happened before. Astronomers think they found, quote unquote, streams of 12 small galaxies that got a little too close to the Milky Way, either were completely absorbed or disrupted in some ways, kind of an artist representation of what that kind of looks like. So the thick disk, in fact, might be the result of those mergers. Remember that kind of like puffier part of the disk of the galaxy? So in a few billion years, the Milky Way is on a course to collide and merge actually with the Andromeda galaxy. This will be a much bigger merger. This will be much more disruptive to the galaxy as a whole, not to individual systems or individual stars. So when that happens, this Milky Way Andromeda collaboration will probably end up being something like an elliptical galaxy, which that is something we will talk more about next week. The last thing I want to go over is the types of stars that we see in the Milky Way. And I'm not talking about the stellar classifications we've talked about a few weeks ago. This is kind of a more general thing, and it's measuring different things. So the first type of star we see in the Milky Way is what's called a population 1 star. So these are found only in the disk, and they follow nearly circular orbits. So the sun is a population 1 star. Pop 1 stars have a wide range of ages. They could be 10 billion years old, they could be 5 billion, they could be younger. What's important is that these stars have a relatively high amount of heavy elements in them. These stars have between 1 and 4% of their total stellar mass made up of elements heavier than helium. Population 2 stars are found throughout the galaxy, some in the disk, but many are also in highly elliptical halo orbits. They live in that stellar halo. These are universally old stars, typically between 11 and 13 billion years old. And importantly, these stars have much lower abundances of heavy elements. So a typical value would be 1/100th of the amount found in the sun. So much, much lower. So the idea behind this is that Pop 1 stars are made from material in a universe enriched with metals. And remember, in astronomy, a metal is something heavier than helium. So Pop 2 stars died and ejected metals into the universe, and those elements went into making Pop 1 stars. So that's why Pop 1 stars have more metals than Pop 2. So this implies a population of stars we will call population 3. These are the first stars in the universe and made entirely of hydrogen, maybe a little helium. When these stars died, they provided the material for Pop 2 stars. So we haven't found a population 3 star. Um, these would exist in the very early universe, and we just haven't been able to observe them yet. But the theory is that they are out there. Okay, so that was a quick introduction to the Milky Way. Be sure to read the chapter for some further explanation and let me know if you have any questions.